Hello everyone, welcome to the AI Harvard track of ValleyML AI Conference 2022. I'm Pratik Sharma. I'm a design engineer at ON Semiconductor, and I'll be co-chairing the AI Harvard track along with Moto Ikiyashi from Intel. We have several interesting talks lined up for today. Let's begin by thanking our sponsors. Our platinum sponsors are Habana, the gold sponsors are Phoenix, Edge Impulse, and CogniFiber, and our silver sponsors are Applied Brain Research and Verda. Few housekeeping items. Please submit your questions through the Who's Q&A feature. You can submit your questions anytime during the session, and we'll get to them after the pre-recording ends. You need to scroll down to the bottom of the page to press the button to enter the live Q&A session.
Our next speaker is Dr. Eyal Cohen from CogniFiber. Dr. Cohen is the CEO and co-founder of CogniFiber, with over 20 years of industrial and academic background in the fields of photonic computing, hardware design, neuroscience, and algorithms development. CogniFiber is a unique deep tech startup company developing innovative photonic computing systems that can accelerate AI applications by more than 100-fold. This will make artificial intelligence more accessible to businesses, hospitals, and law enforcement, leading to financial growth, improved life quality, and even saving lives through accidents prevention. Today, Dr. Cohen is going to present CogniFiber Aurora, the fastest, most efficient AI accelerator.
Hi, I'm Eyal Cohen. I'm the CEO and co-founder of CogniFiber, a photonic computing company from Israel, just 20 minutes east from Tel Aviv. First, I want to thank the organizer, David, Karen, and Koji for the great conference. We've been here face-to-face last week. We had great time, great feedback. We had great connection and hopefully future collaborations. And we are very happy to be here also at the virtual conference, take part of this great conference, which speaks about AI, promotes AI in a very professional level. So before we get to our presentation, I want to share with you two short movies to help you understand. This is about complex new technologies. So these movies might help us better understand, to give you the feeling of what we are going to achieve. Thank you, and join me in these movies.
Ever since the von Neumann architecture was invented, computers have been tirelessly reading, writing, and processing data at exponential rates. We have reached a point that this computation model is no longer sustainable. Having reached its speed, performance, and energy consumption limits, creating a computation bottleneck on a global scale. And yet we expect to leverage AI to extract reality-altering insights from data. But hold on, because things are about to change. With CogniFiber, the way of the future today. CogniFiber introduces pure photonic computing at the speed of light, using light itself, shattering all existing barriers. CogniFiber's revolutionary computation solution biomimics the brain's computational efficiency, but does so at photonic speed. With artificial neurons and synapses forming multi-layered neural connections, using fiber optics and optical communication components, achieving the impossible by building deep neural networks that learn as they process, harnessing the reliability and efficiency of optical communication to create the ultimate photonic neuromorphic computation solution that can outperform the most advanced processors by 1,000 times in every way, with a fraction of the energy consumption by taking AI to the next level. CogniFiber, envisioning an energy-efficient world at speeds that are light years ahead of our time.
Thank you. As you've seen, this is a very ambitious plan we have, and we are getting forward every year. In this ValleyML, we wanted to first launch our second very important step of a first full system of pure photonics. Before we get to the intricates of how do we do it exactly, where we're gone about, I'm going to show you just another small movie about the product itself. Here it is. Thank you for your patience. And now we are going to get to the main presentation. I wish all of you a great listening. And beyond that, please contact me afterwards. We really want to collaborate and promote AI at photonic speeds and efficiency. Thank you very much. Hi. I'm Eyal Cohen, the CEO and co-founder of CogniFiber. I would like to thank the organizer for having us on this great conference. We had a great face-to-face last week, and I hope you enjoyed this one as we are enjoying the company and the talks and the speakers. We are CogniFiber, so we are doing photonic computing for AI applications. When I finished my PhD 8 years ago in neuroscience, I was not only a neuroscientist lecturing about the brain, but I was also an engineer who worked in startups, in hardware, algorithm, machine learning, and I wanted to do something that actually could change the world for the better when I finished my PhD. When we looked at the world of AI from the eyes of a brain neuroscientist, brain researcher, we looked for several issues, and eventually we set ourselves a very ambitious goal to have computing system based on photonics, which are not only 1,000 times faster, but also at least 100,000 times more efficient in order to induce sustainable future for AI computing. This, of course, will also dramatically reduce costs for user, allowing many businesses to access AI without having great expenses. So when we started 8 years ago, the basic limitation of AI hardware were quite, let's say, obvious for everyone. The bandwidth was not good enough, the cost was high, and generation of heat and using a huge amount of power were already shown, and the trend was worsening. Back then, it was only 1% of the total energy consumption of the world. Today is 2%, and it was expected to rise up to 10%. And today, if we look at AI models, they're really getting higher. Today's most popular transformer models are huge. Some of them are even more than 100 billion parameters large. And they take weeks to months to train with a huge cost of 5 to 10 and even more millions of dollars. And the carbon footprint is huge. Some say it's more than a car all the way to the moon and back, or you can measure it for how many cars are riding on the road. But anyway, if we look at the general trends today, so we use larger and larger models to increase AI accuracy. And of course, in some cases, we need very high accuracy, for example, autonomous vehicles. But on the other hand, as the models grow, the ability of the AI hardware to keep up in pace, going lower in terms of how many operations per second, full operation they can do with such large models. And you need larger and larger hardware to support it. This hardware is also having higher costs in terms of immediate cost, but also power consumption, and of course, larger carbon footprint. So these trends are not very optimistic for AI in the future. So how we're gonna deal with that? We looked for this answer 8 years ago already, and looking how can we replace the traditional electronic chips, which actually I really like, and coming from that industry and know how efficient it is, how good it is, and reliable. But still, for AI, we need a lot more connectivity, and also to solve system level bottlenecks, but also chip level bottlenecks that limit bandwidth, like memory bandwidth, and PCI bus bandwidth, etc. So the natural step was to look for similar solution, scalable, integrated systems like silicon photonics and photonic integrated system, who emerged very beautifully from MIT labs and other labs in the past decade. And these are very nice chips, but when you use them in coherent fashion with the same laser using phase, like Mach-Zehnder interferometers for computation, then you are prone to phase noise. And this is very hard because there's a lot of sensitivity in the system. And this was the major obstacle of photonic computing all the way in the past 30 years. And the other thing is, when you want to scale up to millions and hundreds of millions of parameters, the size of the chip becomes really enormous. And then you have issues of yield and scaling and power consumption as well. So what could we do? I mean, we really wanted to have a photonic solution, and the only thing photonic that seems to work well was optical communication. And optical communication is not only industry that exists for already more than 40 years, very robust, using very high speeds and low power devices, but also, as we could see it, fiber is much more natural conveyor of light with far better efficiency compared to others. So how could we use fiber or fiber-based devices, keeping the advantage of fiber-based interfaces, which give us huge speeds of input-output, while doing it in an amplitude encoding without phase, so removing the issue of phase noise. And of course, our major challenge was how to do it in a scalable manner in terms of size. So if we could have very large room for the computing itself, like a room size system, that's not a problem. We can build it. But if we wanted to scale down, that would be the major obstacle to, let's say, to bring these systems into smaller and smaller sizes for application which are not in data center alone, edge application, for example. So if we look at today's optical fiber, we can see that there are what's called multi-core fibers. So it's many cores with a single fiber can actually be used already in usage today in optical communication. We have the many 12 cores out there on the shelf. And of course, in optical communication, you want to avoid the crosstalk noise. So each of the cores is a separate channel, about 20-30 microns, at least apart from each other, in order to reduce crosstalk noise. And this is how you can have an image, every pixel injected in, for example, if we scale up, and you can have the same image at the output. And these types of fibers are also used for imaging in healthcare. We have many applications in the future. But we don't want just to shift data from one point to the next. What we want is to compute. So how do you use multi-core fibers in order to create processors which are very efficient and are photonics based? What we do is have some of the cores closer to each other and actually to enable crosstalk noise. If we can control the crosstalk noise we can have, in a control manner, we can have a function over the inputs, over the vector of inputs. If it's an image, we might be able to say what's in an image, or to, let's say, detect anomalies within an image. And it's a similar problem like controlling the current from a drain to source in a transistor. So the question is, how do we control these crosstalk interactions? By the way, even today, NTT, the giant networking from Japan, showed that they can use crosstalk noise actually in the multi-core fiber to enhance SNR of communication. And that's very interesting, because normally we avoid it, and we see that we are not the only one that try now to use crosstalk noise as a form to actually get benefits from the fiber, let's say, transmission. So how do we control this crosstalk noise? First, we control it in a fixed manner. When we produce the fiber, control the, let's say, the distances between the cores, and this of course controls the amount of crosstalk. Of course, during the when manufacturing, there's about 2 to 3% of noise. So even if we want to have about half a micrometer apart the cores, between half a micrometer to 1 micrometer, probably we have some small deviations, but we actually showed that this could be dealt with. So we can group some of the cores into small groups that can talk to each other and propagate the light to other groups. That's the fixed control of light flow and the interaction between the cores. And the second form of control is the dynamic control. So like in FPGAs, or like in firmware over ASICs, we want to have a dynamic control of the calculations, but also the routing of the light between cores. And that we do using amplification. So the signal we use is regular communication signal, 1550 nanometers, and we can amplify using having some of the cores being erbium doped. And we can inject a second wavelength called the pump light in the wavelength of 980. And this will amplify the light in some of the cores. We can inject exact amount of amplification light to each core and have specific amplification. So we can control, and this amplification could be both linear and nonlinear depending on the amount of pump light. So if we have a small amount of pump light, we can have the linear amplification. For example, then we can implement, for example, bias and weighting. But if we are on the nonlinear, let's say, work point of the amplification with a lot of pump light, we can have nonlinear function to help us implement a ReLU or sinusoidal function, a nonlinear function for the activation function. So that was the basic idea, and what we showed back then, like we published it in 2016 in a Nature paper, a scientific report, that we can introduce a 4-layer network with 24 inputs and 6 outputs into a single multi-core fiber having 72 cores, which is not very much. So taking these 4 layers networks and with its synapses and neurons and arranging it inside a multi-core fiber will give us the functionality of the network. Just to give you an example, today in Fujikura, Japan, they can make a multi-core fiber with 100,000 cores already today. So these are not erbium doped, but we might be getting there in just a few years. So how do this network or computation over this network actually occurs? We have the input here in pink and the output here in gray, but how do the light propagate from the input to the output here in the center? So for that, we did a small demonstration. Of course, we use many simulations to simulate this propagation within the fibers using highly reliable software, commercial and used for industry software. And what we show, what we shown in the paper, that if you inject the light at the input layer, at the input of the fiber, when the light propagates through the fiber, it doesn't only propagate in the z-axis, but it actually propagates also the xy axis, going from one core to the other because of the crosstalk. So the crosstalk moves the energy of the light between the core, such the whole energy moves from one core to the next, from layer input layer to the first layer, and then to the second layer, and all the way to the output layer. And this takes few centimeters, but we can play with it. We can make it longer or shorter, depending on the distance between the cores. So this was the basic idea. And what was the actually, what does it say? It says that if we inject using fiber optics with regular communication wavelength, we can inject many cores, each of them at very high speeds. And if we amplify each of the nodes such that it will implement a neural network with its weights, biases, and function and nonlinear functions, we can get at the output a computation of a neural network. And in the paper, we actually showed it. We showed that we can identify specific pattern over other pattern using the amplification pattern as a trained, like as if it was trained by an algorithm. And we showed that this identification of pattern is possible. So you can imagine how great speeds could be injected and what great efficiency, both in time and energy, because the speed of compute is just the speed of light going through the fiber, and the loss, because of it's a fiber, is really minimal. So the efficiency is huge here. So now when we look at the future, we want to see how we exploit this possibility. If we have, if we can use 100,000 cores, like in Fujikura, Japan is using, but let's say in an hexagonal shape processor. So can you imagine a processor with the size of 2-3 centimeters wide, about 10 to 20 centimeters deep, and this is a full network with 6 ports around it as inputs and outputs. And since photonic processors do not disturb each other, there's no interference like in photonic and electronics, we can put one next to the other very closely in this beehive formation. This allows us, on one hand, to introduce great speed of input, as far as easily 20 terabits per each system. But of course, optical communication already thinks about 400 gig and 800 gig per second. And we can even introduce more than 100 standard fibers for each system. So it could be as far as several hundreds of terabits per second as an input to the system. And by putting them one next to the other, we can have huge computing system, 1800 processor or even more. We can see we didn't use the bottom part, but it could be even scaled to more. But to think about such a computing power one next to the other, this almost goes to the level of a photonic brain. And that was the inspiration, of course. Each of these processors can process at huge speeds in computation of about 2.4 petaflops in these speeds and the amount of elements. And we assume that out of the 100,000 cores, we use about 10,000 as elements in the networks. And the whole system would use up to 20 kilowatt. This is really a very rigorous and conservative computation of the energy we needed because of the great efficiency of fibers. That means an efficiency of more than 1,000 TOPS per watt. When we talk today about computers, normally in small system, we talk about 1 to 2 TOPS per watt. That's in chip level. On the system level, normally it drops down to 0.5 to 0.1 TOPS per watt. And for supercomputing, normally the numbers are 0.05 to 0.02 TOPS per watt. So we mean more than 10,000 improvement of the efficiency, and that means sustainability. Of course, in the future, these will be fully programmable. I mean, the user could program any type of neural network, and this would be programmed using the prompt light to each of the processors. Of course, the user can use any language of control and programming, like PyTorch, Jupyter, etc. And they won't know whether their software is being implemented on GPUs, CPUs, or photonic computing. So this is a vision. It's very ambitious, and we are streaming for that. And I'll talk about several of the steps we made in order to get there. So in general, the company was founded 4 years ago, had already a seed and a small Series A, but in terms of IP, we have already 30 patent applications, and we had a very good experience with Intel Accelerator in the beginning of the company, and we have a very good support of our investor, Charter Group from Singapore. So the first POC we showed, this was the seed period of the company. We had a first challenge to show that this type of thinking of neuromorphics in fiber-based devices is actually possible. The first challenge was to synchronize the inputs into the photonic system, and we used an FPGA-based board. In this case, it was first the RTX7 FPGA from Xilinx. We communicated the data using the client and algorithm from a PC via 1 gigabit Ethernet into the FPGA board, and the data was then transmitted via standard transceivers into the photonic system. And again, to synchronize these transceivers is now a mere fit, because normally transceivers are independent creature. Each of them is a separate channel without any synchrony in clock or phase. And we managed to synchronize both of them in clock and phase and get a 4-channel input into the fiber-based device. And here you can see the first fiber-based device, 7 input, 7 output, that we manufactured together with a company based in New Jersey called Chiral Photonics. And this was implementing the first, let's say, photonic body of our neuron, actually setting the ground for 7 neurons in parallel with common inputs, up to 7 inputs. But because of the limitation of our transceiver, we used only 2 neurons, 2 outputs. Each of them went through an amplifier, erbium dope-based amplifier, fiber amplifiers. These are standard amplifiers, just to show the principle. And this, of course, went back to the receiving side of the transceiver. So we have 4 digital channels multiplied by 4 weights, which were implemented by VOAs that using attenuators, which were controlled by the FPGA. The FPGA also controlled the amplification level. And then the attenuators multiplied in an analog fashion the digital input, and these were introduced into the fiber, amplified, and went back to the receiving side. The speed of the first system was 0.5 gigahertz for each channel, altogether 2 gigabit per second for a single neuron. Of course, not the fastest, but still very good start. What we showed is we can get what we wanted, an activation function. So we could did a linear multiplication of the inputs to sum them up, and then have a nonlinear function compared to the output. And this is the probability in y-axis, the probability to receive a logical 1 from the output. And we can see something between a sigmoid and a ReLU function. We could actually make it more ReLU or more sigmoid function depending on the amplification level we used. We can also play with the bias of the function. But you can see we got a bit, like a lot of noise that's around the function. But we asked ourselves then whether this noise is truly detrimental, or we can use it with the noise at the network level to produce commercially relevant results in the network level. So what we did is took this function and embedded it in a very large simulator of ResNet 18 and ResNet 50, and ran a benchmark of ImageNet. the results we got, of course, we needed in the emulation to use many cores in order to get over the noise and also to reliably implement the filters of Resident 18. So, and still with very large system emulated, we could do 0.5 giga operation per second. That's 0.5 giga images per second. We got an accuracy of about 90%, top 5, and estimated power back then 45 kilowatt. That would give us 11,000 images per watt, which of course is far better than existing technology, but still the accuracy compared to GPU-based cards, one of the best than the Titan RTX, was still low. So we gave up some of the bandwidth and repeated each computation 3 times. We got better accuracy with comparable accuracy and still very good speed up factor, but also in better efficiency. With a high accuracy, we got 160x in speed and 80x in efficiency. If we were satisfied with the 90%, we can have 480x in speed and 240x in efficiency. That was our result, saying that even with the noise, we can actually use this kind of neuronal photonic neuron to get good computation. Of course, this is a very large system, very large feat. There's a lot of setbacks to build it and to use it. We want to scale down and to have a better SNR. So after let's say the last 15 months or so, we're building the next step, which was far better activation function, far better reliability, but also a full network in the first time using the same approach. So of course, we don't compute yet in a fiber, because this, what I told you about the multi-core fiber is a technology that will take a few years to develop. But in the meantime, we are showing that our approach, which is a pure photonic approach, that injecting the data directly in the photonic system and just reading out without any memory read and write on the way, is still a very relevant approach and could be implemented even with simpler technologies. So what we launch and present in ValleyML at this point is the second step, and an important step toward our first product as well, which will be an autoencoder, and based on this technology. And again, we use an FPGA board to control the data flow and also the parameters of the network. In this case, we use analog lasers instead of transceivers. So it's a bit slower. Instead of 0.5 gig, it's 100 megahertz. But again, because of our approach, the clock of the input is the same clock of the output, and it's the full task clock. So every clock, we have a vector of data injected into the photonic system, and we have the full computation. So our 100 megahertz clock is the task clock, so we make 100 million full tasks every second. And what's more, the size of the network is independent, of course, on the speed and the size of the input. We can make it as deep as we want without affecting anything at the input level. So we can have larger and larger networks beyond this demonstrator. So with this demonstrator, it's a 4-layer classifier. Each layer contains a weighting array, again, using the VOA, the optical attenuator. And we use this time an analog electro-optical neurons to take the sum, the result of the weighted sum, and go through a nonlinear function in this case. So each layer has its own server service shape weighting matrix, and a server shape array of electro-optical neuron. And what we show is we can create this pure photonic system in a small enough shape, and again do 100 million operation, and the efficiency, as I said, is very good. In this case, a 300 watt only for this full system. Still is a very small network, a classifier, and we need to scale it up to make it commercially available. And the future, the two future, let's say, immediate challenges that we want to meet is first, increase the speed, coming back, probably going back to transceivers at gigahertz speeds. And the other hand, to replace the analog electro-optical neuron with fully optical neurons that allow, again, gigahertz speeds. And then we can, again, boost both the speed and the efficiency. What can we do with an autoencoder? An autoencoder is a small network, about 5 layers all the way to 9, 11 layers, depending on what you do, but 5 layers is the minimal. And still with very low amount of parameters comparatively, could be tens of thousands of parameters. We can do anomaly detection, we can denoise data, do dimensionality reduction, and generate synthetic data using GANs, the autoencoder as a GAN. So we focus now on anomaly detection, looking for partners and POCs and future clients, but we are open to use all the other functions as well. Today, we are focusing on industrial IoT and cybersecurity and fintech, but again, autoencoder is a very wide usage across all verticals almost. Of course, anomaly detection is a very wide function, can be used in many, many cases, and again, have a high commercial relevance. So if we look at our future beta coming out in about 12 months, we aim for a 50 gigahertz per channel. The expected wattage will be about 2.9 kilowatt, which is comparable to Lightminder server, but a bit half of what NVIDIA uses. Of course, in the future, we'll need to scale this down as well. You can see that it gives us a very nice X in both cost and efficiency, and a reasonable rate density. Of course, this is not our, let's say, vision, but it's only meant to show that our approach, the neuromorphic pure photonic approach, which is a neuromorphic analog approach, is commercially relevant even at the early stages. In the coming year, we'll be launching our beta, and then, of course, later on, we'll look for customers. And in parallel, we want to promote also our next pure photonic. So the company is advancing actually a 2 arrowhead. On the one hand, we want to reach the market and not be just a company having a research with a very far vision, but no contact to the actual ecosystem it serves. So talking to clients, talking to the industry, understanding the needs, understanding the necessities, and having products out there is very important for any commercial company. And as I said, anomaly detection for these verticals will be our first target. But we talked about our far-reaching vision, and for that, we want to reach both computer vision, NLP, e-commerce, smart cities usage, also communication usage for 5G and 6G. But for that, we'll need, as I said, additional technologies. We'll probably use other technology like laser scribing, probably do some silicon photonics. For example, if we want to have the training being fully optical, we probably will use silicon photonics based integrated circuits. We can also use 3D printing and polymer based fibers, all in order to reach this final goal, which we expect the first prototypes to come about 4 years from now. Of course, to do this feat, you need to have an excellent team. And we indeed do have an excellent team in CogniFiber with world-level expertise in photonics, optics, hardware, software, and AI. And just to give you an, the last year was amazing, designing the system and building it, testing it. and I'm sure we're going to do great with this team. And of course, when we expand, have again more very talented engineer, and we encourage you to come and join us in the next phase of the company. So that was it for CogniFiber. I want to thank you for your attention. Ready for your Q&A. I know it's been not 45 minutes, but I'm sure that Q&A will fulfill the next 20 minutes. I'll be happy to join you and answer your questions. Thank you very much.
Okay, thank you, Eyal, for the great talk. So let's start with a few questions. Do you have any applications that you can tell us about that this technology or the CogniFiber will be highly useful for?
Yes, so the thing is with current implication that we are aiming for are relatively smaller networks that can do autoencoder based computing. This includes, for example, anomaly detection that is very widely used in cybersecurity, prevention and predictive maintenance in industrial IoT, but also in fraud detection and the control of transaction in fintech. And this will be our first line of products, since this is a quite small networks. And in the future, we are going to gradually grow let's say the depth and the width of our networks, while together including more and more fiber-based devices to reduce energy and to increase efficiency.
Okay, so is it like currently, are you thinking about data-centric applications? Like, will it be used in data centers?
Yes, so at first, we intend to deploy in data centers and also in private data centers, depending on the client. If the client has a private data center, it's a large client, uses a lot of data, we can deploy in the client's data center. If it's a client that uses let's say a hyperscaler, we can together talk to the hyperscaler and deploy our system for his usage. In general, since a single system can achieve very fast speed of computing, it can actually be of service to many clients, doing a circulation with each second can switch between clients and give service to more than tens of clients in parallel. So that will be our objective in the coming, let's say, 12 to 18 months. First, to find POCs using our current system, and then going through beta with additional POCs.
Okay, understood. So how does, have you compared it with some state-of-the-art data centers, or let's say supercomputers, the performance or power efficiency, things like that?
Yeah. So so there's two types of comparison. If we compare the current technology we use, then it's still less attractive, let's say, compared to NVIDIA servers. But since we are aiming to increase the speed of the input, and our input speed is our output speed, it's the same speed. I mean, it's the whole compute speed. Going in the next year to gigahertz regime, replacing electro-optical neurons with fully photonic neuron. That's our main milestones for the next year. And then we'll be more than comparable even to NVIDIA's DGX. And when we get the results of the new H100 of NVIDIA, we can tell if we're still in advantage or not, but we are waiting for their benchmarks. Regarding the future technologies, the in-fiber full networks that I described, that will be starting around 3 to 4 years from now, after a B series, then these will definitely be over 100x over any existing technology, including, if we give any competitor a 10x or a 20x, still there'll be a very large differentiator, both in speed and efficiency. So we are going in step by step, being more and more attractive from every year or every 18 months of additional, investment and a company being advancement in its technology. But the IP includes many patents. We still don't use most of them.
Okay, that's interesting. All right, I don't see any questions in the chat box. Do you have any key takeaways that you would like our audience to have from this talk?
Yes, I think that last week when we're face-to-face in ValleyML was a great opportunity actually to validate what we think. The fact is that any type of a single chip solution together with connecting, let's say, to electronics that today does some of the compute and the chip, the photonic chip doing some of the compute, is limited in its, let's say, acceleration because of inherent bottlenecks. And this is the main challenge we are trying to avoid. Of course, doing pure photonics in an analog manner where the signal goes from layer to layer have the challenges both in terms of size. Then we are going to reduce size. We already started to using glass-based chips in order to reduce size, but also in terms of the signal integrity itself. And that's why we go for the brain to seek additional, let's say, solutions, how to make an analog system that is more like a brain-like and less digital-like. So the whole system is not a von Neumann architecture. There's many challenges that have to do with it, but this Aurora that we present this week is definitely a very important step in getting some of these barriers. And we are going to enjoy the next year or two overcoming the next barriers, because we think for now, it's the only scalable and sustainable solution, giving photonics using photonics to its utmost abilities or capabilities.
Okay, that sounds quite interesting. All the best to your team.
Thank you.
And thank you very much for joining, and thank you all the audience for joining.
Thanks for the organizer. We had a great time in the conference. We hope that everyone takes the best from the conference. We look forward to collaborations and continued talks on this matter. Thank you very much.
Yeah, thank you.